Welcome everybody, this is Team 1, Hacker Kermit team. My name is Hossam Elwahsh. I'm the team coordinator for this sprint. For this sprint we're working on a simple ATM machine, as you can see here. This project uses two ATmegas, 32, one for the ATM ECU port and one for the quad ECU port. This one is responsible for simulating a real banking card and also for verifying the data like the card ban and the PIN number, but not doesn't include the database for our bank. Okay, for this project I was responsible for developing the DIO, SPI and LCD drivers, as well as the algorithm and flow for the application layer for the ATM ECU port. Regarding testing for the DIO and LCD drivers, they were heavily tested in our past projects, so we just ran quick tests on them. For the SPI module, this one was a new one, so for testing I used an echo-like system where the ATM MCU repeatedly send digits to the card MCU, and these digits are incremented every time with a delay of 50 milliseconds. So we can see the code here, this code for the testing part for sending the data. We are initializing the count by 0. You can see that, okay. We are initializing the count by 0, sending this count, showing on the LCD what we are sending right now, incrementing the count by 1, adding a 50 millisecond delay, and when this count reaches 250 it just resets back to 0. This test case can be viewed in our test protocol here, which is the first one. Just the send and receive. This is the sending part. For the receive part, it just receives data from the ATM, which is this one, and then echoes back this data on the next loop. So we can test this real quick here. Okay, as you can see, we can pause the simulation. We sent from 0 up to 21. We can see here the ATM, which is a lower line, sent zeros, and then on the next cycle the card ECU replied with that 0. We sent 1, reply 1, sent 2, reply 2, and this will go on up to 250, and then it will reset back to 0. We can see here from the log we have no collisions or any issues at all. Can also increment, yeah, here we are sending 60. On the next cycle we receive 60 and send 61, and this goes on up to 250. For the second test, we're doing the same, but adding a restart every 8 transmissions. So a minor edit will be done. We restart when the count reaches 8. Let me build this real quick here. Run it again. Yeah, as you can see, we sent from 0 up to 7, which are 8 counts. Then the SPI is inactive, goes active again, and we send the same data back. So the reset function is running correctly. If we change that with a stop, it should just send the first 8 stops as a SPI, and it won't really send or receive anything anymore. So yeah, didn't build, sorry. Let me build here. Run back. Yeah, so 8 is sent. inactive and nothing is sent anymore. The LCD is just running because this is a while loop. So this was pretty much the testing technique for the SPI module. For the hardware part for this project, we took over 12 hours to debug and double check hardware issues, but we weren't able to program anything in one of the kits. As you can see here, we need two kits, 1 and 2. So one of them were working correctly, the other one had issues with the burning our code on it. So it turned out that this kit is malfunctioning, so we will replace it soon, but for now we will submit the simulation board for the project. We are also very confident that our code will run right away when we get a replacement for the broken kit. That's it for now. My teammates will take it from here, discussing the rules and testing techniques for their pod, and I will get back to you at the end of this video to showcase the full application and to run some user stories together, which are also visible here. The ATM tests, we will run it, and also these user stories. Thank you.
Assalamu alaikum, this is Mahmoud Mowafey from team number 1. My role in this project was implementing the timer driver in MCAL layer and also implementing the two-wire interface driver which is known as I2C communication protocol driver in MCAL layer. Also implementing the external EEPROM driver which is receives or which is in the hardware abstraction layer. We can go to our implementation. Here we have I2C implementation. We have I2C or two-way interface init function and to start function to start the protocol, and also we have stop function to send stop it to stop the frame. Also we have two-wire write which is responsible for writing 1 byte to memory using the I2C communication protocol, ending two-wire read with acknowledge and with not acknowledge to get data stored or get data received by this protocol. Also we have get status function to check the last operation via get the data stored in the status register. Okay. Also in the EEPROM or external EEPROM, we have EEPROM init which will initialize two-way interface module and to EEPROM write byte according to the sequence specified from the datasheet of this chip. We want to start the communication by sending start bit, and second we will write the the mandatory sequence for the start for this chip and sending the desired location to store our data. After that we will send 1 byte which will represent the data that we want to save in this location. Also we have EEPROM read byte which is responsible for read the byte or read byte from the specified address according to the sequence needed to read byte. We have firstly start the communication protocol, then we will send the address or sequence or device address again, and with the write operation, and we will send the required location again also. After that we will send a repeated start. Here when we will send a repeated start we will check the status register or get status to check the if repeated start is sent or not. After the get start, we will write or we will send the device address. But in this step, we will send the device address by read operation, not write operation. After that, the device will send to us or send the data to master. So master, we will receive this data, and we will check the data sent or not. After that, master, we will initiate or send a stop bit to stop the communication. Okay. Also, we have EEPROM write array to write string to specified address here. Uh, and also we have EEPROM read array to read array from the specified address here. We can check our program using a small application program. Here we have stored function. We have app start program, and we stored a hello world string inside this location, which is 6D08. We can check it now in Bluetooth. Here we have sent hello world, and we will receive hello world. We can pause program now. Here with the address location was 6D08. We send hello world, and we will read this location again and print the location or the string read it. Print the string. We will print the string using LCD. Here we will call the EEPROM read array, which is responsible to read the string and return a pointer to static function here. Pointer to static array that we initialized here. We have initialized static array, and we will return the pointer for this array to print this using the LCD. Here we print the sending devices. Here we print the LCD string, which is stored string. Okay. Thank you.
Assalamu alaikum. My name is Abdelrhman Walaa. Team 1. In Team 1, in this part of the video, I'm going to discuss my role in the project Simple ATM Machine project. Simply, my role was implementing some drivers in the MCAL module, other in HAL module, and finally, and last but not least, the card app module, or sorry, card app, the card ECU app. In the MCAL module, I worked on implementing external interrupt driver, UART driver. I'm going to discuss some issues and bugs faced me during implementing specifically this driver in MCAL. Regarding HAL module, I implemented the buzzer driver, keypad driver, and that's it in HAL module. What issues I faced in the UART drivers, simply I used to implement my drivers that uses pulling methods, a timeout mechanism. I mean, any driver, or sorry, any API that that needs to use the pulling method, I take in consideration implementing a timeout mechanism. So that wasn't the case during implementing receive byte API. Why? Because this specifically this API needs to pull until receiving a byte, and implementing a timeout mechanism will will cause a corruption in the string received during receiving the string. So instead, I used a blocking mechanism, and this this actually consumed time. I was expecting to implement it in 4 hours, but actually it takes around 5 hours. That's all my rule. Thank you. Thank you. Assalamu alaikum. In this part of the video, I'm going to discuss test cases scenarios on the right part on card ECU application. Regarding the card ECU, okay, first of all, we're going to run our project. The virtual terminal is waiting for our, for input. We're going to choose second mode, programming mode 1. Okay, we're going. It asks for the card pin. First test case scenario: enter more than 19 digits. So these are 20 digits. Okay. As expected, not invalid range message pop out. Second one, less than 16 digits. We can enter 1, 2, 3 only. Also not invalid range. Third test case, we're going to enter a pen with alpha characters. Can run 1, 2, 3, L. Non-numeric, wrong pen, non-numeric message popped out. Okay. Fourth one, we're going to enter a correct one. These are 19 digits, which is in the valid range. In the valid range. So pen is saved successfully. Message popped out. He asks now for the pin. First test case scenario in the pins. A pin with less than 4 digits. Okay, 1, 2, 3, and this 1, 2, 3 also. Not wrong pin, not 4 digits. Okay. More than 4 digits. 2, 3. The sixth one. Sixth one, more than 4 digits. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Also not expected output is not 4 digits, and actually the output is not 4 digits. The seventh one, a pin with alpha characters, we can enter 1, 2, 3, L, 1, 2, 3, L. A message wrong pin, non-numeric expected, and the actual one is wrong pin non-numeric. Different confirmation messages, confirmation pin. This one can be 1, 2, 3, 4, and 4, 3, 2, 1. The confirmation one, I mean, non-identical. Wrong pin is expected, and the actual is non-identical wrong pin. The ninth one, to enter a correct pin expected output, he will ask for the confirmation pin. This is the case above. 1, 2, 3, 4. 1, 2, 3, 4. Unexpected. This is the 10th test case. An expected pin is saved successfully. Message will pop out. And this is what happened actually. Pin is saved successfully. These are all test cases scenarios on the card ECU. They ran as expected. Thank you for your time, and Assalamu alaikum.
Well, welcome back again. This is Hossam. In this part of the video, I will be running a quick full project simulation with you, and after that we will discuss it in more details, and also we are gonna run the test cases and user stories from our test protocol sheet together. So starting off, this is our internal database, and also the card here will simulate this account. This is the balance for the account, and it's also not blocked. Okay, so starting the simulation, we have the welcome screen, and it will wait for a code to be inserted. We can simulate that with the terminal here. So we already have data, so I'll use user mode. So now we have our code. Now for the PIN code, the PIN code for this account is 4606. Long press to enter. Now it's verifying, retrieving our data. Okay, now we can choose an amount. So the balance again is 5,805. We can say we can withdraw 1,500. Long press on enter. Please wait. Approved. Our new balance should be on the screen now. 4305. Okay, ejecting and welcome again. This is a quick test for the whole system. We can now run our test cases. So for the test cases, we have 4 test cases for the ATM ECU. The first one is to check the inputs, meaning the keypad and the enter key, before inserting a code. So expected that there will be no action. Let's try that out together here. So no chord in the system. So pressing the keypad, hold the keys, does nothing. Pressing is 0, does nothing. Long pressing this should simulate an enter. It also does nothing. So this test case is okay. So no action. Second test case, to enter the PIN number 3 times wrong. Expected that the system logs out and the buzzer or the alarm is on until system reset is done. Okay, so we're gonna insert the same card. Our PIN code is 4606. We'll enter something different, like 1239. First trial. We get wrong bin, 1 out of 3. Next time maybe 4 zeros. Enter. Wrong bin, 2 out of 3. 9876. Should log the system now. So wrong bin, 3 out of 3. System logged, the buzzer is on. You can see here it's high. And we can't do anything more until a reset is done. So pressing this does nothing, nothing is working. So this matches the expected. Next test case, that we enter an invalid bin length. Okay, for our ATM ECU, for the algorithm I made, you can't really enter a longer bin. The keypad will not respond to anything more than 4. So we can test adding 2 and trying to long press this. Nothing will happen, and on a release it will act as a 0. So a 0 here. Okay. Trying to input any more after entering 4 digits will do nothing. Okay, until you press enter, and that will be a wrong pin. Okay, so this also matches the expected. Okay, and for the last test case that we enter the correct pin code, which is 4606, which we already done at the start of this part of the video. So the same account, 4606, enter, and we are good. We are in the system, and we can now withdraw money. So these were the test cases for the ATM ECU, or the ATM app module. We're gonna go to the user cases now, or the user stories. So we have 5. The first one is that we enter a card that is not in our database. So we can reprogram the our card here to have some number that is not from these numbers. So here from the terminal we go to programming mode, maybe 1 2 3 1 2 3 7 8. That's a valid length, but it's not in our database. A bin number maybe 4 zeros. Okay. This card is immediately inserted. The bin is 4 zeros. Okay. Okay, whenever we try to withdraw anything, it will just lock out the system and show this message. So this test case matches the expected result. The next case is that we insert a card that is already in our database, but it's stolen or plugged in our system. So we can use this number here to test this user case. So reprogramming. Okay, card ban. We'll be using this number. Okay, 4728459258966633. The pin number 1234. Okay. Try to withdraw anything. Maybe 4,000. Oh, I'm sorry. This is the pin number. Okay. Let me redo this real quick. Okay, same card. Pin is 1 2 3 4. Okay. Okay, here I will try to withdraw 1,000. Stalling code and the system is locked. Nothing will work anymore until a reset. This is the expected. just symbol formatting issue. I'll fix this later. Okay. For the next user story, we will try to insert a valid code, but try to make a transaction that is above the limit. As we can see here, our limit is 5,000. So 5001 shouldn't work. So we will reprogram with a valid chord. So programming mode, we can choose this one again, 494684. I just fast forward this. Okay, another new pin, say 2587. Okay, 2587. Okay, so the account, if we try to withdraw 5001, the balance can cover, but the ATM won't be allowed to withdraw any number more than 5000. So entering 5001 shouldn't work. It won't log the system. It will say max limit exceeded, as you can see, and will ask the user to insert the amount again. So we can also try to add just a half. Shouldn't pass. Okay, so this user story matches the expected. Okay, the fourth one, insufficient fund. Here we will try to withdraw an amount that is below the max limit, but the account doesn't cover it. So we can withdraw 5000 and that will approve, and then we try to withdraw say 900. That shouldn't approve. So let's do this here. Welcome, insert, same chord. I don't really remember this pin number, so let's look into our memory. 2587. Okay, 2. We can resume here. 2587. Enter. Okay, we'll withdraw 5000, which matches the limit, so it should be okay. Transaction approved. My new balance should be 800. Yeah, that's correct. Ejecting. We'll wait for insert. Insert the same code again. So now our code has only 800. We'll try to withdraw 9. Oh, sorry, this is the pin number. Okay. Keypad seems to be malfunctioning here. Okay. Let me check that. Okay, this is a minor bug. We can see in the code here the keypad gets disabled after we enter the amount that we want to withdraw, but it actually doesn't get enabled again. So we'll just fix this by adding an enable to the launch state. So keypad enable, and they're gonna build. That should fix it. I'm gonna retry. So same code, pin number is 2587. Okay. Withdraw 5000. New balance. Ejecting. Insert same code again. 2587. And the keypad should be working. Okay, keypad is working again, so I'm glad this happened with us here, so that we can really discuss it. Okay, now back to our test case. We'll try to withdraw 900. This 9000 will be over the limit, so our system can allow you to write again before pressing the enter, so no problem. Okay, 900 should say insufficient funds. Here we go. Okay, so this bug will be pushed to the final code before releasing. Okay, this one matches. It failed, but we fixed it, so now matches. So the last user case or user story is just a valid card transaction that is not above the limit, and the balance covers it. We already did that, but let's do it again. Okay, same code, 2587. This account has 5800. Just withdraw maybe 3000. Okay, 321459. Okay, approved. Our new balances should eject. Okay, and that was it for our video, and this is the final part of our video. Hope you enjoyed, and thank you.